Today's video is all about coils, or more formally, electrical inductors. And we haven't really talked about inductors before, but we've actually touched on the subject with their properties in perhaps the last dozen videos or so. Well, in this video, we're going to look at the actual property of inductance and see how it works. In a nutshell, inductance is a property of a coil, and in many ways it is the equivalent of resistance for a resistor. In the case of a coil, an inductance is a measure of how much the coil wants to keep the current flowing through it from changing under any circumstances at all. And that is really the most key property of inductors. It wants to keep the current flow steady or constant. Now, we can demonstrate that quite nicely by using a bunch of batteries to give us about 6 volts and taking the contacts from the coil and attaching them to the battery and then pulling them away, and you get a nice big spark. And the reason you get the spark is because when we attach the contacts to the coil like this, current starts to flow. You can even hear the top of the transformer click a bit closer sometimes. And once the current is flowing, if I now break the connection, the coil does everything it can to keep the current flowing, and in fact it generates a voltage much higher than this battery could ever produce. In fact, the voltage it's generating is probably in the thousands of volts. The voltage is so high that if I was careless and were to touch both sides of the wire from the coil while I was doing this, I would get a very nasty shock. So in case you're wondering how much current is actually going through the coil when we're doing these experiments, well, it's about 2 amps. So when we break the circuit and the spark appears, that spark is initially at 2 amps and then drops down rapidly to 0 after it's dissipated all the energy in the magnetic field in the coil. And in fact, that is a key part of the whole thing. There is energy being put in the magnetic field in the coil by the current, and when we break it, that energy has to go somewhere, and it is given off in the energy we see in the spark. So how does all of this work? Well, we've seen these two equations in numerous previous videos. The first one here relates the current flowing through the coil to the magnetic force field, and the second equation relates the resulting magnetic flux to the electric field and hence voltage seen at the terminals of the coil. And in this form, it's not really very practical for dealing with inductances, but if you go through a bunch of math, which we won't bother looking at, you can end up with these two simple equations that summarizes all of this in the form of a value of inductance, typically represented by the letter L. And the inductance, in this case for a solenoid type coil, depends largely on the square of the number of windings or turns on the coil and the area and length of the coil and this magnetic constant over here. The bottom line is, for any particular coil, we can characterize it with a value of inductance just the way we can characterize a resistor with the value of resistance. Inductance is all very well, but what can we do with it? Well, we can use it to relate changing current to voltage. In other words, the voltage we see on the terminals of the coil depends on the size of the inductance of the coil and how much the current is varying. If we have a constant current through the coil, the variation in current is 0, and if the coil had no resistance, we would get no voltage across it. The di dt here is just the calculus way of saying a change in current in relation to time, as opposed to maybe the more easier to understand delta I, or change in current over change in time for a short time period, that if you haven't had calculus you might prefer to use, but it's essentially the same thing. And what we saw in our experiment was we would set up a nice big current going through the coil by attaching it to the battery, and then when we broke the connection, well, we're basically stopping that current almost instantaneously, so we get a very big delta I over a very small delta T, and when we multiply that by some inductance we get a very big V, and that's where the spark came from. So that's what we sort of see for interrupting currents, but for AC currents we can actually end up using the inductance almost like a resistance. And in AC we refer to the equivalent of resistance as impedance, typically denoted by Z, or in the United States Z. And the formula for impedance is J omega L. J is the imaginary number, omega is 2 pi times the frequency, and L is the inductance of the coil. So we get our impedance over here, and just like with Ohm's law, the current is the voltage divided by the resistance, or in this case impedance. So if we can calculate the impedance of the coil because we know its inductance and the frequency of the AC current, we can fairly easily calculate the current flowing through it. And we can even just take this and replace the impedance with J omega L down here, and you might be wondering, well, what does this J mean? Well, the imaginary number J, which is J in electrical engineering as opposed to I in mathematics, we use J because we already use I for current. That J tells us that this current here will be lagging the voltage going through the coil, and it's kind of useful to have it in this form if you have a whole bunch of things like resistances and capacitances also in the circuit. Then the J's all work together to give you a final current with a certain angular offset from the voltage. We won't worry about that here. So that's how it works, and what we really should do is take a quick look at the practical effects of AC on an inductor. What we'll do is attach the inductor to our good old variac here to apply some AC current, and we'll use the clamp-on ammeter to measure that current. With it all connected, let's turn up the voltage. And I don't know how well you could see it, but at 120 volts we had about 1.5 amps flowing through our coil. Now what happens if we take the top bar off our coil? Well, that should reduce the inductance of the coil because it is now harder for the magnetic force field to generate flux through the coil. What that really means is to maintain that 120 volts on the windings of the coil, we need a much stronger current flowing through the coil. So what we would anticipate is in this configuration with 120 volts, we would expect a much higher current to be shown on the ammeter. So let's try it. And there we go. We went even past 20 amps right there, but it was probably more like 15 or 16 amps when we had 120 volts on this coil. So that really does show that when we make the inductance lower, the amount of current that ends up flowing through the coil goes way up, and when we put this back on, the current would go down. I'm not going to do it live because this would clamp on so quickly it would probably squish my fingers, and we don't want to do that. So that was a quick introduction to inductors and inductance. These really are very widely used electrical components, either in big coils like this or in tiny tuned circuits in radios and TVs and other devices. And perhaps today, some of the things you saw in this video, namely the great big spark, is essentially the basis of some switching power supplies like the ones we plug into the wall to power all of our nifty electronic devices. And interestingly enough, historically, those types of switching power supplies were used to generate the 20 to 30 kilovolts used in old CRT TVs, which could generate great big sparks. And if you're interested in that, one of my earliest videos actually covered such a power supply, and I'll put the link up so you can take a look. Anyway, that's the end of this video. I hope you enjoyed it. See you next time.